All right. Well, good morning, everybody. Hope you're all doing well, and I hope those of you in the college at least got to enjoy your wellness day yesterday. Remember, spring break is scattered across 5 days this semester, so make use of your wellness days, please. We will have a few announcements, but I thought I would hang on just for a few minutes for announcements because I know that you're all rolling in still. Um, but we wanted to start by chatting just a little bit about ethical considerations. And the reason, in part, not only is that it's important, but also that we're actually going to be having a discussion about ethics in class on Thursday of this week. One of the things that I've been reflecting on, that a lot of us are reflecting on, is the role of different types of features in our data and when we need to be careful about using those features. One very salient example from history in the US is the use of redlining back in the 1930s, when the US government classified different neighborhoods based on how safe it was to give a loan there. And they color coded maps where green meant it was the lowest risk and red meant it was a hazardous place to make a mortgage loan. And this led to discrimination where there were largely Black or minority populations that were identified in red neighborhoods. And you might think, beyond just kind of the obvious thing, well, that feels discriminative. You might think, well, why is that discriminative? And I think a good place for me to start is to think about stereotyping, right? So what is a stereotype? A stereotype is when kind of attributes of a group are associated with attributes of an individual. And in that case, the viewpoint was that if you live in a particular location, then you share the loan risk attributes of everybody throughout that location. You're not getting down to the individual. And the US government responded, and during the civil rights era, we had laws that were passed to prevent discrimination around race, where we would view location as was used in the 1930s as being an unfair and discriminative proxy because it was being used in a way that was carrying essentially race as a signal and nothing else that was especially important to the decision of the lender. And these things come up in lots of settings. And when we build our learning systems, we need to think obviously very carefully and deliberatively about the role of the data and the model and how it affects things like questions around race. And I wanted to discuss this with Finale because I know she thinks about these types of things in the context of
Yeah,
healthcare.
and actually, I mean, building off of what you're saying, I think that there's just a really important question of like, when is race relevant, or how should it be relevant? Like, should our algorithms be race blind? Should our systems be race blind? Like, oh, we can't use race, so we'll just use location. That was a sneaky way to continue a pattern of discrimination. But I was just talking to a company that's doing a machine learning related rollout of their product, and they mentioned that especially in Europe, they are not allowed to collect race as a variable. And to me, that kind of seemed like a problem in the other way, where I was like, well, how do you know your product isn't discriminatory? They were like, we worry about that, but we don't know. Maybe there's a feature in here that has something that is discriminatory. This is through GDPR and the privacy protections.
Yeah.
Yeah.
Yeah, this is a challenge. There are companies that want to or are legally precluded from using race in a number of different settings like housing, and yet at the same time want to and should want to understand whether their systems are fair or not. That's a challenge.
Right. Yeah. And absolutely. And there's also just thinking about situations where you want to be able to identify bias. Like, I think at the early on in class, we talked about the case where severity scores in healthcare were being underestimated for Blacks because they utilized the system less, and it was just assuming, oh, people who use the system less are less sick. But if you have a group that, you know, has been excluded from the system, they're going to be using the system less. And that doesn't mean they're less sick. It just means that they're using the system less. Whereas there may be other situations where you really do want to include, especially in health, you know, race as a variable, because there are certain biological differences and certain risk factors don't carry across different ethnic groups. And so you end up with risk scores that are trained on predominantly white populations. And then if a Black person has, you know, those mutations, for example, it doesn't mean that they're as high risk for getting the disease as a white person might be. And BRCA gene is a good example of this.
Right.
So, yeah.
So there's a real difference in that case, and you would really want to carry race within the model.
Exactly. It would be very important to do so. So,
yeah,
I mean, I don't know what you think, David. I think it's really important to carry that variable and then check afterwards, rather than to ignore the variable and then.
That's what I also tend to advise. But I know that there's sensitivity to that within companies, because it can also open them up to additional liability.
Yes. For sure.
Potentially. So, but I agree. Great. So on topic of ethics, we just wanted to mention that this Thursday we'll have a guest lecturer who will be leading a discussion on ethics in the context of ML. We've given you some very light pre-reading to think through before class. It shouldn't take you more than an hour, I would say max, but we would like you to just complete a little prompt or two before 8 p.m. tomorrow evening, which will help to guide the discussion in class on Thursday. In addition, really importantly, we posted on Ed yesterday, and we'd like you to complete today your availability for when to take the midterm, which will be next week. So please complete that survey, certainly by the end of the day today, and we'll be using that to figure out how to schedule you into the midterm sessions a week today. Excuse me, a week on Thursday. Lastly, just a reminder that your homework 3 is due this Friday at 8 p.m. We hope that lots of you are looking at it. We're a little nervous because we didn't have many people come to office hours last week, so please do be starting on that homework. I think those are all the announcements. Maybe one more is the midterm review materials will be coming out later today, within a couple of hours. They're basically ready to go. And we'll also be announcing a schedule for midterm review sessions next week. I think that's it. Did I forget anything, Finale, before we dive in?
I think that's everything I can think of.
Okay, great. Any questions before we continue? Okay. So what I want to do next is just remind you where we got to last lecture. We're going to be talking about support vector machines. We're still talking about classification, so we're still up in this point in the cube. And as you remember, we said that we might prefer this decision boundary over this boundary. And you can see that kind of intuitively, it's got a larger spacing to the data, even though it's misclassified this one example down here. So we were talking about these max margin methods, and we got to the point at the end of class last week where we had both a hard margin formulation and a soft margin formulation. So today what we're going to do is we're going to continue to work with these formulations. We're going to be working with a dual of these, and I'll explain that. And we'll get to what are known as support vectors, and we'll see the kernel trick, which is a very powerful way to bring basis functions into machine learning for classification or regression. And as I mentioned last time, support vector machines have a record of very successful applications. They are still competitive with neural networks. They are convex optimization problems to train. They have a coherent theory, etc. So just in a little bit more detail, here was the idea of a hard margin. We were looking to find a separator to maximize the minimum distance to the decision boundary. Here's that margin 1 over the L2 norm of the weight vector W. Here's our margin boundary equal to 1 in terms of the discriminant function or -1. And then what we said is, well, we might also want to relax this. Our data may not be separable. So we talked about the soft margin formulation. And in the soft margin formulation, we allow some examples to float to the wrong side of the margin boundary. So here's an example that is still correctly classified, but the wrong side of this discriminant function equal to 1 margin boundary. And we introduced these CN slack variables to capture when we're making mistakes with regard to the margin boundary. So here the CN is between 0 and 1. This point is on the wrong side of the decision boundary. So the CN is larger than 1. This point's actually all the way over here, so it's larger than 2. And we got to this particular optimization formulation of the training problem. Couple more pictures. We're going to be talking about support vectors today. In the hard margin case, they will be on the margin boundary. In the soft margin case, they will be living inside the margin region. And we'll use those to describe our discriminant function. So here there are 4 what we'll call support vectors. This will be more clear as we get into the mathematics. And we'll also talk about how to bring basis functions in that will allow for non-linear decision boundaries when we project back down to our original feature space. So for example, we'll be talking about basis functions that we'll get in through what we'll call the Gaussian kernel. And this will allow for a non-linear decision boundary. Here's my margin boundary and my margin boundary. Here we set the soft margin penalty capital C to be infinity. So we've captured a hard margin separator. Here we set C to be smaller, and we've got to a soft margin separator. Okay, so that's really just warm up. Hopefully that is helpful as a refresher of where we got to last class. See, there are a couple of questions. How does the dimensionality of the data set affect its chances of being separable? I guess intuitively, higher dimensional will be more likely to be separable, but really we're going to get at that through introducing basis functions to be able to get to separability. And then what were those terms on top of the regularization? Let's see, what did I show you? I don't remember there being terms on top of the regularization. Let me show you the picture again. You're referring to this equation here, Raphael? Yeah, I mean,
no,
I guess
sorry,
I'm not. Go ahead, Raphael.
I think Oliver asked the previous question, but my question was on the next slide, because it seems no points were misclassified, the circular boundary one.
Yeah. So this is, you can see that this is a soft margin formulation because I have a point that's inside the margin boundary, but you're right, all of the points are correctly classified here.
I meant for the
soft margin. I'm sorry, this point is even classified here because it's the wrong side of the decision boundary.
But I meant for the next slide, the one on the circular boundary.
Mm-hmm.
Yeah, it seems no points were misclassified either way.
Yeah, I think that's right. So just because you move to a soft margin doesn't mean you will necessarily have points that are misclassified. It just means that you're willing to kind of, I think if you visualize this, you can see how in the hard margin case, we've worked really hard to fit the decision boundary between these 2 points. And you see how this point kind of looks like an outlier? Whereas when you move to a soft margin, you see how the decision boundary has kind of been willing to move closer to this point. So the way to think about it is that as we go from hard margin to soft margin, we're introducing some regularization and we're working less hard to fit our true data. But you're right, in this particular case, we don't actually misclassify any points, but the decision boundary has moved.
And so what are the dash line in those cases? So
the dash lines are the margin boundaries. So the solid lines are always our decision boundaries. And the dashed lines are always the distance one, are always the points that have a discriminant value of either +1 or -1.
Okay,
So here are my points that have a discriminant value of say -1, and here are my points that have a discriminant value of say +1. So you see how we have some points that are inside the margin region. Does that make sense now? Great. Okay. Thanks for your question. All right. So let's talk some more now about support vector machines. And first of all, just want to recall these two formulations that we were working with. We had our hard margin formulation. And then we had our soft margin formulation. Remember, we have to figure out how to write this Greek letter C. And the point is that in the soft margin formulation, we relax the constraints by allowing the left-hand side now to be smaller than the right-hand side. And when it becomes smaller than the right-hand side, Cn needs to be larger. Okay. So what we're going to do today is one, we're going to solve the dual form of the max margin problem. We'll do that both for the hard margin and the soft margin. And this will allow the discriminant, which is our h function, and this is our discriminant function, where remember that we use that function to decide how to classify an example. This will allow us to write our discriminant function, which so far we've kind of been writing like this, and we've been writing in linear form as this. For these new variables, alphas will be non-negative. So this probably looks a little bit mysterious at the moment, but notice that kind of in place of the, I need a transpose on that. Notice that in place of the weight vector now, I have this kind of linear combination of the examples in my training data multiplied by their training label. Looks a bit mysterious at the moment, but that will turn out to be very powerful. And where alpha n is actually positive, that will be a support vector. And then secondly, we'll talk about the kernel trick, which will allow us to access a basis function. Remember, our basis functions take us from our d-dimensional space into a higher dimensional m-dimensional space. And we'll be able to access that via just a scalar product of, say, the basis applied to, say, example n, and the basis applied to some other example x. And the neat thing that we'll see is that by kind of only using, so the key idea, let me maybe just kind of make this very concrete. We will only use our basis function phi in this scalar product form. And that will turn out to be useful, and you'll see why. Okay, so that's what we're doing today. So let's just remember where we are. What do we have? What do we have in the, dual? What do we have in the hard margin formulation? Where did we get to last class? This is what we have. Our hard margin formulation. And what we're going to do is we're going to write down a Lagrangian optimization version of this, where we're going to introduce an alpha n variable, which will be non-negative for each n. And we'll write down this optimization problem in a Lagrangian form. I just want to comment that you've worked with Lagrangian optimization already in this class. You remember when we had to make sure that the prior probabilities, when we were doing generative models for classification, added up to 1. In that case, we had an equality constraint. In this case, we have so we're going to use a Lagrangian form for an inequality constraint. So it's going to be a slightly different Lagrangian optimization than you've seen so far, because the constraints that we want to kind of bring into the objective are inequalities rather than equalities. And the Lagrangian form that we want looks like this, which I will explain once I've written it down. She has a min-max structure to it. Where this thing here is our Lagrangian function. So this has a min-max form. I'm going to call this formulation A and this formulation B. All right. And my claim is that the optimal solution to A is equal to the optimal solution to B. That's my claim. And I claim it through the following sequence of arguments. 1, an optimal solution to B must satisfy the constraints of formulation A. So let's think about that for a second. And to think about that, we need to understand this min-max structure. So the way to think about this is, suppose that you are player 1 and you are the minimizer. And suppose that player 2 is, and you get to pick the W's. And suppose player 2 is the maximizer. And think about player 1 moving first and choosing the W's. And then player 2 moves second and chooses the alpha values. Player 1 is trying to minimize the kind of result of player 2 trying to maximize. So that's how to think about this min-max. Now, if player 1 makes a choice makes a choice of these W's such that this inequality is violated for one of our examples. What does that mean? That means that the left-hand side is smaller than the right-hand side. Well, if the left-hand side is smaller than the right-hand side, it means that this expression is negative. This expression here, y wx plus w0 minus 1 would be negative. And so you've got a negative in front of this, which means that the maximizer player can drive this whole thing arbitrarily large by choosing alpha arbitrarily large. So claim is, this is the first part of our argument, if the W's are such that one or more of these inequalities are violated, then the maximizer can pick an alpha on those constraints to drive that Lagrangian function arbitrarily large. And this is not good for the minimizer. Not good for the minimizer, right? So that's our first claim. 2, the optimal solution to B sets alpha n equal to 0 on all xn where the inequality is strictly satisfied. So where yn wt xn plus w0 is strictly larger than 1. It's really the same argument. So now suppose that this is strictly larger than 1. That means that this term here within the Lagrangian function is strictly positive. And if the maximizer, and notice that there's a negative sign, so if it's strictly positive, then the maximizer will want to set alpha to 0. Notice the alphas are constrained to be non-negative. So the maximizer is not able to start setting alpha negative. The best the maximizer can do is to set alpha equal to 0. And then the third step of the argument then is that by 1 and 2, the optimal solution to B satisfies alpha n yn wt xn plus 0 plus w0 minus 1 equals 0 for all n. Why is that? Well, by 1, we know that either this expression here will be 0 or will be negative. And when it's negative, we know that alpha will be 0. Okay, so if this is 0, then 0 multiplied by alpha is 0. If this term here is negative, we've argued alpha has to be 0. And so either way, the product of this has to be 0. And so what that means is that in any optimal solution to B, this term here will be 0. Therefore, the objective in B will be exactly the same as the objective in A. So that completes the argument. The optimal solution to B satisfies this and therefore solves A. So I've just walked you through what is, if you were taking a class on constrained optimization, would be described as a sufficiency argument for the correctness of the Lagrangian formulation here. I think it's nice we can kind of argue it the way I just did, and hopefully most of you were able to follow why B is equal to A. Any questions about what I did? And I should have apologized at the start of class. Again, there's going to be quite a lot of like nice but mathy stuff today. And again, as I said last lecture, we will be changing pace after this lecture. And then Oliver's asking, what are we trying to do? Yeah, so it's kind of mysterious right at the moment. So what are we trying to do? We started with this formulation, and I've just argued that it's equivalent to this formulation. Who cares? Why? Why do we care? Not clear yet, but you're about to see why we care. Okay, so why do we care? Well, I'm going to start talking about duality now. So I'm first of all going to talk about weak duality. So Oliver, David, this will probably become clear. Raphael, I can give you a sketch again, but we don't have the time to walk through it in detail again. But I can give you a sketch again of why it solves A. The basic argument we're going to make is that any solution to B must, one, satisfy the inequalities in A, because otherwise this maximization becomes unbounded. Two, if the inequality is strictly satisfied, meaning this is larger than 1, then the alphas will be 0, because the maximizer will want to set the alphas to be 0. Therefore, 3, we can argue that each one of these terms in the optimal solution will be 0. Therefore, they end up not affecting your choice of an optimal solution. You need an optimal solution that satisfies the constraints, and you will choose as the minimizer to minimize this term, which is exactly the term we started with. That's a sketch of the argument as to why they're equal. Good. So now let me mention what I mean by weak duality. What do we have here? We have min W0, max alpha greater than or equal to 0 of this Lagrangian function. That's just rewriting this expression. Where this, I'm writing this whole thing as this Lagrangian function. So this is where we are. We've argued this is equivalent to our hard margin formulation. Now notice that I can switch the orders of the minimizer and the maximizer, and this will only make the maximizer less powerful. What do I do? So I'm going to argue that if you're the minimizer, meaning that you want to make this whole expression as small as possible, you would rather play this game where you move seconds than this game where you move first. So that's why I'm writing the inequality this way. This term will be larger, weakly larger than this term. And I think that's pretty intuitive. Notice what's happening over here is you have to commit as the first player to your choice of W's, and then the second player gets to pick alpha. Over here, the second player has to pick alpha first, and then you get to pick a W that minimizes given that choice of alpha. But I think you should be able to see the intuition for why this inequality would go in this direction. Here, somehow the second player gets to pick a different alpha for each choice of your W. And here you get to pick a different W for any choice of the first player's alpha, right? So that probably that inequality is reasonably straightforward to see. It turns out that, and we won't get into the detail as to why this is true, but it turns out that this problem actually satisfies what's called strong duality, which means that actually the left-hand side is equal to the right-hand side. You can switch the min and the max order without changing the value of the objective or without changing the solution to the problem. And underneath this, there's a duality theory that is out of scope for this class, but it holds because our objective in A is quadratic, and our constraints are linear. And if any of you have seen linear programming and seen the dual of a formulation in linear programming, this is a convex analog of that. So again, you're probably wondering, why are we doing this? Why is this useful? I hope that's what you're wondering at least. So let's recap where we are. I'm just looking at Raphael's comments. Wouldn't you read min-max inside out? No, you should read it outside in. You should read it as the W plays and then the alpha plays. I mean, that's the easier way to think about it. Or at least that's the correct way to think about it. Think about them being brackets. So where are we? We're here. We've now got what is our dual formulation. It has this max-min structure. It's max over alphas, min over the Lagrangian function. This is our dual formulation now. And we've argued that this is equivalent to the hard margin formulation that we started with. And the reason this is useful is that we can now write this in terms of alpha only. We're going to be able to solve for this inner minimization for any choice of the outer alpha values. And the reason we can do that, whereas we couldn't do it with the min-max formulation, is that this inner problem now has no constraints. See how the alphas have to be non-negative? That leads to a problem with using first order optimality conditions. But because the W's are unconstrained, we can use first order optimality conditions to solve for W's for any choice of alphas. So let me show you what I mean. So first of all, for any alpha, the optimal W0 must satisfy, let's write down our partial derivative. So if you take the partial of the Lagrangian with regard to the W vector, what do we get? Hopefully you can see this as I write it. You're reasonably used to doing these now. That's the partial. And then I'm going to set that equal to 0. And that is going to give me the W is equal to this. I remember we saw that in the discriminant function that I gave you right at the start of class. So if I give you alphas, then the solution to the inner minimization problem is to write down these W's, because that sets the first order condition to be 0. And let's go ahead and call that equation star. And similarly, for any alpha, the optimal W0 satisfies. So now let's take the partial with regard to W0. And if you do that, then you get this term. Setting that equal to 0 will ensure that our choice of W0 Notice the W0 doesn't actually appear in this expression. So this means that the alphas, the solution to the alpha maximization, will have to satisfy this equality constraint for the W0 to be optimizing. So we'll take this as a constraint on our outer optimization problem, such that we can ensure that the W and W0 choice is optimizing in the inner problem. So what we can now do, I know it's been a lot of to get to something elegant, but we're about to see something elegant now, is that we can now simplify our objective. So if you take this objective, which was our Lagrangian function, so now we can simplify that objective. So what we can see is, let's just begin first of all to expand some terms. Right now I'm just going to algebraically expand this section. Not doing anything clever yet. This is just a mechanical algebraic expansion. Okay, let's say mechanical algebraic expansion of the earlier objective. And now I can simplify. So notice that by equation star, this is just our parameter vector W. So I've got half W transpose W minus W transpose W. So that's minus 1/2 W transpose W. And then we're going to add this as a constraint into our optimization problem. So because we add that as a constraint, then this term goes to 0. And so what I'm left with is I'm left with this expression. So this is by substituting star and adding constraint. Lastly, we can now go ahead and substitute in for the alphas in place of the W. Because I'm trying to get an expression just in terms of the alphas. There's an expression just in terms of alphas. And now we can bring this all together. And this gives us our dual hard margin formulation. So what is it? Remember what we started with? We had this max over non-negative alphas. And we've just rewritten all of this now in terms of alphas. So I'm going to be able to write this whole thing down as max over non-negative alphas of the summation of alpha n's minus, I missed a minus sign up here. There should be a minus sign there. Make sure you catch that if you are writing down notes. There's a minus sign that was missing there. Minus, and then I'm just going to expand this expression out. And if I expand out that expression, I get a double summation over n prime, alpha n prime, yn prime, xn transpose, xn prime. And then I need to add my constraint that alpha n yn equals 0, and that alpha n's are non-negative. This is my dual hard margin formulation of my SVM training problem. And I will pause in a second and take questions. I see there's been quite a lot on chat. But let me also just mention that there's a soft margin formulation where all that I do is, in place of that, I allow C, I insist that my alphas never become larger than C. And it turns out, we won't work through the derivation of that, but it turns out that that equivalently gives me the soft margin dual formulation modified by introducing C. Okay, so let's see. Hopefully Finale's been able to keep up reasonably well, but let me pause and take questions about anything I just did. I wasn't able to see all of the things flashing by, so maybe go ahead and raise your hands or type your question again if you didn't get your question answered. Max, please.
Hi, sorry, I'm still a little confused about why we're allowed to impose this constraint. I thought that this would be the optimal W's for a given choice of alpha. So why can we impose this constraint that the, what was it, that the alphas times the y's must go to 0? Like if we picked alphas such that that wouldn't be the case, wouldn't that mean that that wasn't the optimal, like we just wouldn't have an optimum for W naught? I'm confused about how we can go the other way.
Yeah. So we want to make sure that the W naught that is kind of implicit here. I didn't solve for W naught yet, but we want to make sure that the W naught we solve for will be optimizing. And so we're adding a constraint to the choice of alphas to make sure that we will be satisfying that partial with regard to W0. I think the way you said it is right. If this constraint wasn't satisfied, then there would be no W0 that is optimizing. So this will allow there to be a W0 that is optimizing.
But wouldn't that potentially mean that you could get a higher maximum if you didn't have to abide by that constraint on your alphas? Wouldn't that allow you to achieve a higher maximum in terms of what alphas you choose?
It's really going to make the problem bounded. The problem is if we don't have this, then the objective will not be bounded. Okay. What other questions do people have? Go ahead and either type your chat or raise your hand. Okay. So then I just want to make a couple of comments and then we'll take a little breather. So a couple of comments. One, what is my discriminant here? Well, we know what that looks like. It looks like this, because remember the star equation told us what the weight vector looks like in terms of the alphas. So that's what my discriminant will look like. Now we get to this concept of support vectors. So the support vectors are the set of alphas that are strictly positive. That's what we mean by a support vector. It's an example for which the corresponding alpha value is strictly positive. And as a picture, here's my hard margins. Again, here's my decision boundary with discriminant value equal to 0. Here's my margin boundary with discriminant value equal to +1. An example that is up here, remember we argued that when we were talking through the structure of the Lagrangian, that an example that's up here for which the boundary constraint is holding with a gap relative to the right-hand side, that will have an alpha value equal to 0. It must, for that minimizer to be doing what the minimizer wants to do. But an example that's on the boundary, the optimal solution may or may not use a strictly positive alpha value there. May or may not. Okay, so we know that if alpha n is strictly 0, then the example is on the margin boundary. So that's the picture for the hard margin case. And then the picture for the soft margin case is very similar. Here's my decision boundary. Here's my margin boundary with discriminant value of +1. It's still the case that if a point is on the right side of the margin boundary, that the corresponding alpha value will be 0. It's now the case that a point on the decision boundary may be non-zero, but will be, it turns out, we don't show why this is the case, but will have an alpha value strictly smaller than C, and that any point that's inside the margin boundary will have an alpha value equal to C. Okay, and I haven't explained quite why that detail is true, but this just turns out to be true for the soft margin formulation. And so then what do we know here? We know that if a point has alpha value between 0 and C, then the example is on the margin boundary. And the reason that I'm emphasizing all of that is that then you can see how we can solve for W0. Remember, because we've added that constraint, there will be a small solution for W0. And what do we know, recall that Yn, do you remember that that has to be equal to 1 for an example on the margin boundary? That's how the margin boundary is defined. And so we can find any xn on boundary and solve for W0. That's how you would back out the value of W0 once you've worked with your dual solution. Okay, that was a lot. I think this is a good point to take a short breather. You can shake out, go get some tea, go get some water, or ask me a quick question while we take a short breather. And you may still be wondering, well, why is any of this useful? And we're about to talk about why this dual formulation is now useful and powerful. If you do have any questions, feel free to ask me at this point, just while we regroup. Charu, please.
Yeah, I had a question from like the very beginning of class when you showed like the hard and soft, like in your slideshow when you showed like the hard and soft margin, like the hard and soft boundary classifier. And I was like, I noticed that in the soft margin one, the margin sizes on different sides of the decision boundary were different, like were different. So in one of them it's like thicker, and the other one it's smaller. So why are we allowed to have different margin sizes? Wouldn't the decision boundary be drawn in between both the margins, like exactly spaced?
So first of all, it's a little bit tricky to think about this when we project back down into the original space. You have to be careful because the distances visually are not being correctly maintained. So that could be tripping you up, right? So we just need to be a little bit careful about that. Do you see something that's confusing you on this picture? Because here there's no basis function being used.
Okay, no, that looks good. So we're always guaranteed to have the same size margin on either side of the decision.
Yeah,
Okay.
yeah, that's right. So yeah, I think the thing that's visually confusing to you is maybe it looks like somehow the distance here is different from the distance here, but it's because of what's happening with the projection back down into the lower dimensional space.
Okay, thank you.
Yep, of course. Okay. So we just did a lot of fancy math, and you're probably all wondering, why did we do all of that? Why is any of that useful? So let's ask that question. Why is the dual formulation useful? Okay, why is this useful? Well, let's bring in basis functions. So consider the basis function mapping from d-dimensional space to m-dimensional space. I can just drop that in to what we've, Andy says, can you please scroll back to the end for a moment? Yeah. Okay. All right. Why is the dual formulation useful? So I'm just going to drop that into the formulation that we had. Remember that when we move to a basis function, it's just like we replace x with the x in that new space. These n's and n primes are summing over our examples. And now, rather than x's here, I'm going to write our basis expansions. So I just dropped in the basis function. I still need my constraints. And let's think about this in the case of the soft margin. So I've got my capital C there. And similarly, the discriminant becomes, this is what we actually use to make our predictions once we've trained our model. By the way, the results of training here, if that wasn't clear, is the alpha values. The alpha values are the parameters of the dual formulation of the model. So similarly for the discriminant function, we write this down. Now, here's the crucial observation. Crucial observation is that we only need what we'll call a kernel function to be able to work with these expressions. So what is a kernel function? A kernel function is the inner product on the projections according to function phi of these two vectors here that I'm writing, x and z. And I want you to notice that the basis is only coming into the training problem and the discriminant through this kernel function structure. And we'll say, we will generally will say that these are kernelized. Okay, we'll make a verb out of that. This is the kernelized form, because we can think about writing this just as k of xn x, and this is k of xn prime. And what is the kernel trick that I promised you? The kernel trick is to compute k. The crucial thing now, so pay attention. The crucial idea now is that we can compute the scalar product without going into the high dimensional space. This is known as the kernel trick. You shouldn't see yet how this can be possible, but I'm now going to show you examples of how you can kind of access the basis, this high dimensional space, without actually having to take the x's and the z's into that high dimensional space. So it's kind of like if this is my original space, and I take an x and a z, and you kind of think about expanding that into some larger space through my basis function phi. And I want to take the distance in that high dimensional space. I want to take the scalar product in that high dimensional space. I'm going to be able to do that without actually taking x into that space and taking z into that space. And this is all possible because the only way that the basis function comes into the training problem and the discriminants is in this inner product way. Okay. So how can we actually calculate these kernels without going into the high dimensional space? Let me give you an example. This is the quadratic kernel. Quadratic kernel is this. Notice that it's only doing the calculation in the lower dimensional space. It's taking the inner product between x and z and then squaring the result of that inner product. So let me illustrate this. Let's try to understand what this is doing in a basis space by just thinking about the simple case where x and z are in R squared. So x is vector x1, x2, and z is vector z1, z2. And let's just push through the math. So what is my kernel calculation? It's this. What is that? It's so I have to take the inner product and square it. And then what do I get by squaring that? Well, you all know how to do this. You get this. And look what that is. That's this. So what just happened, this now corresponds to a basis that uses all degree 2 terms. So we just argued that by taking the inner product and squaring the result of that, you have equivalently taken the inner product between x and z, where you've written out all of the degree 2 terms in the x vector and all of the degree 2 terms in the z vector. And so even though we did math without going into the higher dimensional space, right, this is the only calculation we actually did, it's equivalent, it's as if we went into the higher dimensional space. And moreover, if I'd have written this down, then this would correspond to also including the linear and constant term in the basis. So now you add a constant and you add x1 and you add x2. Just by slightly kind of changing the function by adding a 1 in front of it before we square it. And I won't work through the details, this is in the section notes, but just as another example, you can generalize this to what's called the polynomial kernel, where you do to the power q for any integer q weakly greater than 2. This is the polynomial kernel. And if you take q to the 3, q to the 4, you include all of the multinomial terms up to that power. So if you think about it, so this is including all terms up to degree q, just as we showed them using q equal 2, took the terms up to degree 2. And this is very powerful because it's as if the basis has d to the q, kind of order d to the q terms. So we're getting this exponential power in the basis representation, even though we're doing very simple mathematics on the original vectors, on the original feature vectors. And that's why this is so powerful. I'm going to give you another example, and then we're going to wrap and move towards concept checks. So just one more example is the Gaussian kernel. This is for bandwidth parameter lambda. So this is taking the L2 norm of the distance between x and z, squaring it, negating it, exponentiating it. You've seen this type of thing before. This decays exponentially. Think about these as being distances between x's and z's. This decays exponentially in the squared distance. And interestingly, we won't show this, but this corresponds to an infinite dimensional basis. And you might think about, and I think maybe I ask you to do this in the concept check, you may think about whether kind of how this changes. You've seen things like this before when we did k-nearest neighbors and the kernelized non-parametric methods at the start of the semester. You may think about what happens as lambda gets large or small. So I want to make just a couple of comments, and then we'll move to concept check. So notes, one, we can also do kernel engineering. So this is the question, is a valid kernel function? Because so far I kind of showed you examples of kernel functions, and I kind of argued, at least in the quadratic case, that it maps to a quadratic basis function. But how do you know that your kernel function, which is a function on two feature vectors, how do you know that it's a valid kernel function? Where, remember, valid means that it corresponds to the inner product for a basis function. And the answer to this is given by the following theorem, which is to recognize that kernel function K can be considered to define a kernel, also called gram matrix, on data x1 through xn. What do I mean? Think about your pairwise combinations of data where, and we'll write the matrix with an underline K to distinguish from the kernel function, where the entry n prime in that matrix is just given by the kernel function applied to the corresponding pair of examples. And just want to mention that there's a theorem called Mercer's theorem that says something beautiful. It says the kernel function K is valid, meaning it has a corresponding basis function, if and only if this gram matrix is positive semi-definite. The proof of this is way out of scope of this class, but I want you to know that this gives you a way to test whether or not your kernel function corresponds to a basis function, is valid. And the test is the gram matrix positive semi-definite? Now that still seems weird. How is that helpful? How can we know that kernel function gives a positive semi-definite gram matrix? That's not really where the power is. The power is that this lets us reason about how we can combine together kernel functions. So if you have kernel function, so now this allows for engineering. So suppose you have valid kernel function K1, valid kernel function K2. If they're valid, it means that their gram matrices are positive semi-definite. And then by properties of positive semi-definite matrices, you can then reason that all of the following are also valid kernels. And this led to an explosion in support vector machines being used within machine learning. You can take your kernel and you can multiply it by a scalar, and that will be valid. You can take one kernel and you can add it to another kernel, and that will be valid. You can take your kernel function and throw it into a polynomial function. You can exponentiate your kernel function. You can pre-multiply it and post-multiply it by any function f. You can keep going, and by reasoning about the positive semi-definiteness of the gram matrix implied by these operations, you can argue that these are all valid. And it led to a lot of work developing kernel functions. Okay. Right. Yes. So that's implied by what I'm telling you, Raphael, although it's out of scope to see why that's the case. Okay. So I know we covered a lot of things in today's lecture. Hopefully you've kind of seen enough to be able to then go through the notes either in the book. The notation is very consistent with the notation I've just used, or the notes I've just shown you. Again, the reason that the dual form is so powerful is that now we can train in a way where we're not working directly in this potentially very large m-dimensional space. Instead, we're working in this n-dimensional space. Remember, the parameters of these alphas on the training examples. So what I'm going to do is, for those of you that want to stick around just for 5 minutes, I know we're at the end of our official time, I'm going to do a quick concept check. So let me show you that here. I'm going to do a quick concept check. Maybe, Finale, you can be setting up the rooms for me. The first question is, in a hard margin support vector machine, the support vectors are, you need to choose one of those answers. The second question asks you to look at this data and shows you a linear decision boundary and asks you to think about the Gaussian kernel on this data and think about how the decision boundary might change. The third question asks you how you can determine whether a support vector machine is overfitting. And the last question asks you to say a little bit about what the kernel trick is. And it may look like magic, but the correct answer is not magic. And I'm just going to try to share the form with you all. Okay, so there's the form. We'll send those of you that are still hanging out into breakout rooms, and we'll bring you back in a couple of minutes.
I love SVMs.
Yeah,
It's so cool.
they are really beautiful. They're also kind of a lot to cover in one lecture.
It's all too, yeah, also true.
So they are beautiful. And powerful.
Yeah, I dropped in the chat how, like, I think with some neural models now we can operate on funky structures more easily than we could before. But even so, I mean, when all you need is a kernel function, then you can be like kernels over patient trajectories, kernels over maps, kernels over all sorts of funny inputs.
Right.
Are workable.
Yeah. Yeah. And this idea that you can combine kernels.
Yeah.
It's very powerful.
Yeah, I think the reasoning about the maxes and mins is always difficult in terms of the material. So,
yeah.
Very cool.
Beginning to get a few answers. I'll wait a little longer though. All right. So your answers to question 1 were pretty evenly split, but with most of you preferring either a subset of points on margin or inside, or a subset of points on margin. I guess they're in a sense technically equivalent, because remember that in a hard margin SVM, there are no points inside the margin. So the preferred answer, I think, would be C, a subset of points on the margin boundary. But if you said B, that's also technically correct. The thing I want you to realize is it's not necessarily all of the points on the margin boundary, but we know that if alpha is positive, it must be on the margin boundary. So that's the way that goes. That was question 1. Question 2, I guess there's most support for answer 3 or 4. Very little support for answer 1. And yeah, the correct answer is either 3 or 4. When you bring in a kernel, which we do here through the Gaussian kernel, the decision boundary will change because it now no longer needs to be linear. So it will change. And it will change even if there was a linear even if there was a linear boundary that correctly classified. In this case, this linear boundary is not correctly classified. And then the question is whether small lambda or large lambda will overfit or underfit. And I see. So both of these answers are actually correct. This is not a particularly well-written multiple choice. These are both correct. Small lambda will tend to overfit. Large lambda will tend to underfit. So you got it right if you said C or D, and if you're having a hard time choosing, they're both correct. The way to think about it is that as lambda gets, the way I like to think about it is when lambda in the denominator gets very large, then kind of these distances all get washed away, and we tend to not really pay attention to the points very close to each other. Whereas for small lambda, we really tend to pay attention to the points that are near an example, and that tends to overfit. Okay, third question. How can you determine if a support vector machine is overfitting? You can choose more than one. And some support for cross-validation, yes. Cross-validation is always a great way to determine if a classifier is overfitting. And then a little bit more support for choice 1 than choice 2, and that's right. So I guess the intuition here is that if you have a lot of support vectors, then you're paying more attention to your training data. Remember, the support vectors are associated with your examples in your data. So the more support vectors, the more attention you're paying to your training data, which tends to lead to overfitting. And then lastly, the kernel trick is, let's see, how much support for magic? Some support for magic, and it certainly looks like magic. And then most support for choice 2, which is the correct answer, and very little support for the logistic loss. That's right. We didn't talk about logistic loss at all. That's not the right answer. And it's not about avoiding over or under fitting. If anything, the richer the basis function, the more likely you might be to overfit. So if anything, the answer would go against answer D. So I hope that helps. Again, apologies for running a little bit over today. Thank you for those of you willing to stick around. And I'm happy to answer any follow-on questions you have.